Let's get this thing wrapped up. So we're going to do a proof for arc length, and we are going to do an example problem. And then it's up to you to go through and solve, use all of those integration skills, because we're about to pop out an integral. So let's go through the proof, which you're not responsible for, but you try and hang on, see what the heck's going on as best you can. And we're going to use a lot of stuff from previous, since we're talking about arc length, we've already done arc length. We know how to find that in terms of x's and y's. But now we have parametric equations where our x value is some function of t and our y value is some function of g, which means if we have some sort of curve going from A to B that we're trying to, oops, I went a little too far. Well, we have to change up how we think about everything since it's in terms of t. Like look down below. Our x values are f ofs and f ofs. So we're going to want to go through and approximate first the length of the arc. And then we're going to use integration, mean value theorem, all kinds of good stuff to figure out the actual value. Okay, so what we're going to do is like we did every single other time before, we are going to look at just one small piece and approximate that. So I just want to call that some L sub k. All right, some length in between f of t of sub k minus 1 and f of t sub k. Just some interval in between, right? We're getting better with that subscript. Just got through series and sequences. Feeling good. All right, so let's kind of draw it out. Huh? Wouldn't this be like a right triangle? We could approximate the length of this. And we could say, well, this is just the change in y, the change in the height, right? The change in the x. And let's assume it to be positive. We can use absolute values, but let's not get crazy with the notation. But actually, I got to get a little nutty with the notation. I got to put it in sub k. It's all right. So we're going to say we want to get this length. Well, cool. It's the Pythagorean theorem. Square root of a squared plus b squared. So squared plus the change in y sub k squared. Neat. We have one little line segment approximated. Now, this little purple curve we did is not, or line is not the same as the curve. The curve's actually above it, right? When you have your triangle here, the curve is above it. But if we add all these up, we start adding them up, and then we make the interval smaller and smaller and smaller. That's how we get to integrals. So let's start to do that. Let's say like, okay, I want to add them all up from k equals 0, and let's go up to some number n. I don't know what that n is. It doesn't matter. L sub k. Well, that's just equal to our sum. K equals 0, x sub k squared. Now I'm going to jump to this next step. By the mean value theorem, there is some point in between a and b, or t of k minus 1 and t of k, such that the derivative is equal to the slope. Sorry. But we could change this thing up. I'm going to lose this part here and just write in the sum is k equals 0 to infinity. And let's just say it's x prime. X prime f prime of t sub k all squared. And our y is now a g. G prime of t sub k squared. Now if we let the limit as, oops, I wrote an infinity up there. Oops, that would have actually been equal. Oops, I'm so sorry. But now if we were to say, let's do the limit as n tends towards infinity of this infinite sum, f prime of t sub k squared plus g prime of t sub k squared. We're going to find that the length is from a to b, the square root of f prime of t. Now you can drop the k's. squared plus g prime of t sub k squared. And I jumped over a lot to try and just simplify this down. I don't know whether that made it worse or better, but 5 minutes in, we now have ourselves a formula. Oops, and there's no sub k here. Once you integrate it, you don't need the k's. It's now just t's because we're not adding up a bunch of sums. All right, so let's jump down to our formula, and it's telling us if you want to find the arc length for curves defined by parametric equations, it's the derivative on your x. And you can think of it this way. I like that a lot. If you want to find f prime, it's called x prime. You want to find y prime or g prime? Come on, please work thingy. There we go. So y prime is equal to g prime. Just make it a little simpler. So for myself, I look at this thing. It's like, I don't like all the y's or the f's. X prime plus y prime squared, just to make it a little less notationally dense. But I do like to keep that d at t, letting us know. Oh, did I not write that before? Bad teacher. Bad teacher. Goodness gracious. I guess it's been a while. We've been dealing with sums. I've forgotten about all of our notation. I hope you don't. All right, I guess I'm going to be like, do as I say, not as I do. What a dick. Okay, let's do an example problem. Sorry for my language. Let's talk about an asteroid. Let's find the arc length of an asteroid. Maybe not the asteroid you're thinking of. Where x is equal to some number. I don't know what that number is. Oops. I'm so used to that muscle memory. A times cosine cubed of t, and y is equal to a times sine cubed of t. And let's just look at this thing from 0 to 2 pi. Now let me show you what an asteroid looks like. We'll just grab it now. Remember, I'm not necessarily masterful in the arts of graphing. It's kind of like the unit circle. You get some points, but except it's going to go like this. An asteroid. It actually has to do with the idea of taking a ball on a point right there, and if you were to rotate it this way as it rolled up the hill, kind of strange. That's where that point would end up being. I'm going to shut up. And that would be if it was enclosed in a circle. But let's get out of that. All right. That's what it looks like. Okay? Where we don't seem to have defined quadrantial angles, right? Like it's 0 and pi over 2 and pi and 3 pi over 2. It looks like we have sharp edges where it's probably not going to be defined. So let's see if we can't find the arc length, but I want to show you how we could have done it. Now, I'm not going to make you do this. I'm not going to make you do this at all. But I could ask you to parameterize this and just write it in terms of x's and y's only. So if we were to divide out our a's, let me get that stuff away. We'd get cosine cubed of t, and then we could hit it with a cubed root on both sides and say that this is cosine of t. And then the same thing would have happened over on the other side. I'm just going to jump to it. Sine of t. And then we could play that same game that cosine squared plus sine squared is equal to 1. And then we pop this stuff back in there. And do you mind, I don't like the way that's written. You know, why are we writing like that? Well, we could write in a much simpler way that's easier for doing work, you know? So now we can replace that stuff in and say it's x over a to the 1/3, but it's squared. I'm cheating. 2/3. And then it's going to be y over a to the 2/3 is equal to 1. Right? Sine squared plus cosine squared equals 1. Same game. And they're both got the same value. It's not an a and a b, it's just an a. That's what makes it all symmetric and stuff. Oh, let's do this. Let's find the length of the curve from 0 to 2 pi, where a is equal to 1. Let's keep it mellow. Let's keep it mellow. Well, how do we do this? How do we take a derivative on this dang thing? Well, we're going to go right to here. We're going back up to the top. We're going to use these formulas. We didn't have to do that. That was just to kind of see what's going on. And this is actually how x over a, or this point here, a comma 0, 0 comma a, negative a comma 0. Yeah. All right. We looked at it, but now we don't have to any longer. Like on an exam, I would probably just ask you, what's the frickin' arc length? You don't need to graph it. I'm just doing a terrible job of explaining it, you know? I'm trying to explain it, but I don't think I'm doing a very good job. My apologies. So now let's get into it. Let's do a good job on what you're going to be responsible for doing. Well, we know that the arc length is a to b. We're going from 0 to 2 pi. That's what that's going to be. And then we're going to find the square root of r. And let's just call it x prime of t squared plus y prime of t squared. Now we don't have to use all those f's and g's and then get confused with that. That's how I like to do it. That's why I was like, f's and g's at the beginning. Like, I need to show you. We need to talk about it, but not so important. So let's go through and let's go find our derivatives. So x prime. We're just looking at this, so won't the 3 fall? You get 3a, and now you're left with cosine squared of t, and then we're just done, right? There's no such thing as a chain rule. There's no such, yes, there's a chain rule. That's going to be negative sine of t. And now what's y prime? Same thing, 3 is going to fall. You're going to get, oops, come on, machine. 3a sine squared of t. And then we have to do the derivative of the inside, which is cosine of t. And we found x prime and y prime. Now we put all that stuff together and we solve. So let's get it. Oh man, this is going to get big. So we're going from 0 to 2 pi. But oh my goodness, that's going to be one of the worst ideas ever. I'll show you in a second why. And we're going to take the square root of those frickin' derivatives we just found squared. So our x prime, that goes in there. Oh my goodness, right here. Negative 3a cosine squared t sine of t. Now we're going to place our next one in there. Ooh, 3a sine squared of t cosine of t, and all that stuff is squared. My goodness. We have a big problem, though, before we start when you're doing these lengths of curves. Sorry, my asteroid sucks. If you're on the unit circle, you know, pi over 2, 0, pi, 3 pi over 2, and 2 pi. If we're on the unit circle, those are the values of t that we're using. We're using circular, which we'll learn more about soon. 2 pi and 0 are the same gosh darn thing. You plug this in, you're going to get 0 every single time. So we have to use logic. You see this? The interval we're going from, 0 and 2 pi. When you plug that into sine and cosine, you're going to get the same exact value. You're only going to get 0. We have to use logic on this. So anytime we're going to be doing this with an arc length, and we're going around in a circular, you see 0 to 2 pi, there is symmetry to this. There's symmetry. We can say it's 4 of these lengths here. And we can go from 0 to pi over 2, where we actually get different values. So we're going to say 4 times the integral from 0 to pi over 2 of, and now we go. So remember that anytime we're going circular, and you know this teacher loves trigonometry. If you're not seeing this coming, ooh, you're so getting trigonometry. You want to get practice with it. All right, let's get this done in 14 and a half minutes. We're almost done. All right, so let's square everything up. So we're going to get 9a squared cosine to the 4th sine squared. Right? Just doubled up all the frickin' exponents. Good. plus 9a squared sine to the fourth of t cosine squared of t. Now let's, oops, I keep not writing my gosh darn dt. Wow, I'm out of practice. Okay, so 4 times the integral of pi over 2. Let's do some factoring. See, there's a 9 in common, there's an a squared in common. But there's also a sine squared and a cosine squared. There's a sine squared and a cosine squared, so we're going to yank that out. So we have 9a squared sine squared cosine squared, I'm writing my dt before I forget it, times. We would be left with a cosine squared and a sine squared. We'd be left with a cosine squared plus a sine squared. That's just 1. So that goes away. Let's say 4, 0 to pi over 2, square root of 9a squared sine squared cosine squared dt. But they're all being multiplied together. Look at that 9. Screw all that noise. You mean 3 squared? Why did I even change it? So now for 0 to pi over 2 of 3a sine t cosine t. Didn't I say a was 1? Why was I taking that a? Oh, dang. We didn't need that a. It was just 1. We could have done this without even... so if there was a number, it would have gone along for the ride, wouldn't it? What if a was 4? You would have had 12 sine t cosine t dt. Sorry about that. Now we can integrate that, can't we? We can integrate that, can't we? About as simple of a frickin' U sub as you can get, huh? And let's go. So this is equal to 4 times the integral of 3u du. Let's change our bounds of integration. Sine of pi over 2 is 1. Sine of 0 is 0. So we're going to get 4 times 3u squared divided by 2. Evaluated from 0 to 1. That's times 2. So it looks like we get 6 u squareds from 0 to 1, which is equal to 6. 17.5 minutes. What a jerk, but that's your last one for this section. I know it's a lot. I know I did a terrible job of explaining it, but that's the best I can do right now. I hope some of it follows. And if you have any questions throughout your homework, please make sure to reach out. I'm happy to help you out. I'm a lot better with single problems. So, yeah, I feel like I did a lot of talking in circles, but hope it helps.